When we talk about measuring time, most people think about the watch on their wrist or the clock on their wall. But deep inside research laboratories around the world, scientists have created something far more extraordinary. These are quantum clocks, sometimes called atomic clocks, and they represent the absolute pinnacle of human precision engineering. These remarkable devices are so accurate that they would not lose or gain a single second even if they ran continuously for billions of years. To put that into perspective, if you had started one of these clocks at the moment of the Big Bang, approximately 13.8 billion years ago, it would still be accurate to within a single second today. This level of precision is almost impossible for the human mind to fully grasp, yet it is absolutely real, and it forms the backbone of our modern technological civilization. To understand how quantum clocks achieve this incredible accuracy, we need to dive deep into the strange and fascinating world of atomic physics. Everything in the universe is made of atoms, and atoms themselves are composed of even smaller particles. At the center of every atom is a nucleus, which contains protons and neutrons bound together by the strong nuclear force. Surrounding this nucleus are electrons, tiny particles that carry a negative electrical charge. These electrons do not orbit the nucleus like planets around a star, despite what simple diagrams might suggest. Instead, they exist in what physicists call quantum states, occupying regions of probability around the nucleus. Here is where things get truly interesting. Electrons can only exist in very specific energy levels around an atom. They cannot have just any amount of energy. Instead, they are restricted to certain discrete values, like steps on a ladder. An electron can be on one step or another, but it cannot exist between steps. This is one of the fundamental principles of quantum mechanics, and it has profound implications for how we measure time. When an electron moves from a higher energy level to a lower one, it releases energy in the form of electromagnetic radiation. This radiation has a very specific frequency, determined by the difference in energy between the two levels. The key insight that makes atomic clocks possible is that this frequency is incredibly consistent. Every atom of the same element will produce radiation at exactly the same frequency when undergoing the same electronic transition. It does not matter where the atom is located, what temperature it is, or when the measurement is made. The frequency is a fundamental property of that type of atom, as constant as any physical quantity we know. This is fundamentally different from mechanical clocks or even quartz crystal clocks. A mechanical clock relies on the regular swing of a pendulum or the oscillation of a balance wheel. These mechanisms are affected by temperature, humidity, air pressure, wear and tear, and countless other factors. A quartz clock uses the vibration of a quartz crystal when an electric current is applied, and while this is far more accurate than mechanical timekeeping, the crystal's properties still change slightly over time and with environmental conditions. But the frequency of light emitted by an atomic transition is utterly constant, set by the fundamental laws of physics themselves. The first atomic clocks were developed in the 1950s, and they used cesium atoms as their timekeeping element. Cesium was chosen for several important reasons. First, cesium atoms have a relatively simple electronic structure that makes them easy to work with. Second, and more importantly, cesium has a hyperfine transition that occurs at a very accessible microwave frequency. A hyperfine transition involves not just the electrons, but also the interaction between the electrons and the nucleus of the atom. In cesium, There is a specific transition between two hyperfine levels of the ground state that produces radiation at exactly 9,192,631,770 Hz. This number is so important that in 1967, the international scientific community decided to redefine the second itself based on this transition. 1 second is now officially defined as the duration of 9,192,631,770 periods of the radiation, corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. Let me walk you through how a cesium atomic clock actually works. The process begins with a source of cesium atoms, typically an oven that heats solid cesium to produce a beam of individual atoms. This beam travels through a vacuum chamber toward a detector. Along the way, the atoms pass through a region where they are exposed to microwave radiation. The frequency of this radiation is precisely controlled and adjusted to match the cesium hyperfine transition frequency as closely as possible. When the microwave frequency exactly matches the atomic transition frequency, something remarkable happens. The cesium atoms absorb the microwave photons and transition from one hyperfine state to another. The clock contains a detector that can distinguish between atoms in different states. By monitoring how many atoms make the transition, the clock can tell whether the microwave frequency is too high, too low, or exactly right. This creates a feedback loop. If the frequency drifts slightly high, fewer atoms will make the transition, and the control electronics will adjust the frequency downward. If it drifts low, the adjustment goes the other way. The microwave oscillator is constantly being corrected to stay locked to the atomic transition frequency. The output of this oscillator then drives a counter that ticks off the seconds, each second corresponding to exactly the right number of oscillation cycles. The beauty of this system is that the atoms themselves serve as an absolute frequency reference. They are not affected by the same environmental factors that plague other timekeeping methods. The cesium atoms do not wear out, they do not change their properties, and they produce exactly the same frequency whether the clock is brand new or has been running for decades. However, the original cesium beam clocks did have limitations. The atoms in a beam are moving quite fast, and this introduces what physicists call Doppler broadening. When an atom is moving toward the microwave source, the frequency it perceives is slightly higher than the true frequency due to the Doppler effect. When it is moving away, the perceived frequency is lower. This spreads out the resonance signal and reduces the precision of the frequency measurement. Scientists developed several techniques to overcome this problem. One approach is to use what is called Ramsey interferometry, named after physicist Norman Ramsey, who won the Nobel Prize for this work. Instead of exposing the atoms to microwaves continuously, Ramsey's method uses two short pulses separated by a drift region. The atoms interact with the first pulse, travel through a region with no microwaves, and then interact with the second pulse. The quantum mechanical interference between these two interactions produces a much sharper resonance signal, allowing for more precise frequency measurements. But even with Ramsey interferometry, the fast-moving atoms in a beam clock still limit the ultimate accuracy. The solution to this problem came with the development of laser cooling, a revolutionary technique that earned its inventors the Nobel Prize in Physics in 1997. Laser cooling uses carefully tuned laser beams to slow down atoms to incredibly low velocities. The basic principle relies on the momentum carried by photons. When an atom absorbs a photon, it receives a tiny kick in the direction the photon was traveling. When it then re-emits a photon, it receives another tiny kick, but this time in a random direction. By arranging laser beams so that atoms preferentially absorb photons when moving toward the laser, scientists can gradually slow the atoms down, extracting their kinetic energy photon by photon. Using laser cooling, scientists can reduce the temperature of a cloud of atoms to just a few millionths of a degree above absolute zero. At these temperatures, the atoms are moving so slowly that Doppler broadening becomes negligible. This opened the door to a new generation of atomic clocks with vastly improved performance. The Cesium fountain clock represents one of the major advances enabled by laser cooling. In a fountain clock, a cloud of laser-cooled cesium atoms is gently tossed upward through the microwave cavity. The atoms rise, slow down under the influence of gravity, stop momentarily at the top of their trajectory, and then fall back down through the cavity. This gives them 2 passes through the microwave region, similar to Ramsey interferometry, but with a much longer time between pulses because the atoms are moving so slowly. The longer interaction time translates directly into a narrower resonance and more precise frequency measurement. Cesium fountain clocks achieve accuracies on the order of 1 part in 10 to the 16th power. This means it would take about 300 million years to gain or lose a single second. These clocks now serve as the primary standards for international timekeeping, maintained by national metrology laboratories around the world. The coordinated universal time that governs global communications, navigation, and countless other systems is based on an average of these cesium fountain clocks. But as impressive as cesium fountain clocks are, scientists have pushed even further into the realm of precision. The latest frontier in timekeeping involves optical atomic clocks, which use electronic transitions that emit visible or ultraviolet light rather than microwaves. The advantage of optical transitions is that they occur at much higher frequencies, hundreds of terahertz compared to the 10 gigahertz range of cesium hyperfine transitions. Since the precision of a frequency measurement improves with the number of oscillation cycles counted, moving to optical frequencies offers a potential improvement of 4 to 5 orders of magnitude. Optical atomic clocks use atoms like strontium, ytterbium, or aluminum, chosen for having narrow optical transitions that can be probed with extraordinary precision. The technical challenges involved are formidable. Measuring optical frequencies directly was essentially impossible until the development of the optical frequency comb, another Nobel Prize-winning innovation. A frequency comb is produced by a special type of laser called a mode-locked laser, which produces extremely short pulses of light at regular intervals. When analyzed in the frequency domain, this pulsed output appears as a comb of evenly spaced frequencies, like the teeth of a comb. By carefully controlling the spacing and offset of these teeth, scientists can create a direct link between optical frequencies and microwave frequencies, allowing optical clock signals to be counted and compared. The current record holders for timekeeping precision are optical lattice clocks, which trap atoms in a regular array formed by interfering laser beams. This lattice creates a series of tiny potential wells, each holding a single atom or a small group of atoms. The atoms are held almost perfectly still, eliminating motion-related effects that would otherwise limit accuracy. The lattice is designed to be what physicists call a magic wavelength, meaning it shifts the 2 energy levels involved in the clock transition by exactly the same amount. So the transition frequency itself is unaffected by the trapping light. Strontium optical lattice clocks have achieved accuracies approaching 1 part in 10 to the 18th power. At this level, the clock would take longer than the current age of the universe to gain or lose a single second. These devices are so sensitive that they can detect the gravitational time dilation predicted by Einstein's general theory of relativity over height differences of just a few centimeters. Time runs slightly faster at higher altitudes because gravity is weaker, and modern optical clocks can measure this effect with exquisite precision. Another approach to optical timekeeping uses single trapped ions rather than clouds of neutral atoms. An ion is an atom that has lost or gained 1 or more electrons, giving it a net electric charge. This charge allows the ion to be trapped and held in place using electromagnetic fields, isolated from nearly all external disturbances. Single-ion clocks using aluminum or ytterbium ions have achieved comparable precision to optical lattice clocks, with each approach having its own advantages and challenges. The implications of this extreme timekeeping precision extend far beyond the laboratory. Our modern world depends on accurate time in ways that most people never consider. The global positioning system, which billions of people use daily for navigation, relies fundamentally on atomic clocks. Each GPS satellite carries multiple atomic clocks on board, and the system works by measuring the tiny differences in arrival times of signals from multiple satellites. Because these signals travel at the speed of light, even a nanosecond timing error translates to a positioning error of about 30 centimeters. The accuracy of GPS depends directly on the accuracy of its atomic clocks. Telecommunications networks also depend on precise timing. Modern digital communication systems multiplex many signals together, sending information from thousands of users over the same physical channel. This requires exquisitely precise synchronization so that different signals do not interfere with each other. Financial systems rely on accurate timestamps to determine the order of transactions, which can be worth millions of dollars when markets move quickly. Power grids use synchronized time signals to coordinate the phasing of alternating current across continental distances. Scientific experiments in fields from radio astronomy to particle physics require precise timing to correlate measurements made at different locations. As optical clocks continue to improve, new applications are becoming possible. One exciting area is relativistic geodesy, using clocks to measure the shape of Earth's gravitational field. Because time runs at different rates at different gravitational potentials, comparing clocks at different locations can reveal information about the mass distribution underground. This could potentially be used to detect underground resources, monitor volcanic activity, or measure changes in ice sheets and groundwater. The same sensitivity to gravity that enables geodesy also creates challenges for defining time itself. If two clocks at different heights run at different rates, which one is correct? This question has led to proposals for redefining the second based on an optical transition, which would require developing international standards for how to compare clocks at different locations and gravitational potentials. The scientific community is actively working on these issues, and a redefinition of the second based on optical clocks may happen within the next decade or two. Looking even further ahead, scientists are exploring clock concepts that could push precision even further. Nuclear clocks would use transitions in the nucleus of an atom rather than in the electron cloud. Nuclear transitions are much less sensitive to external perturbations because the nucleus is so much smaller and more tightly bound than the electron orbitals. One promising candidate is an isomeric transition in thorium-229, which has an unusually low energy for a nuclear transition, making it potentially accessible to laser spectroscopy. A thorium nuclear clock might be 10 times more accurate than the best current optical clocks, though significant technical challenges remain before this becomes practical. The quest for better clocks has driven advances across many areas of physics and engineering. Laser technology, vacuum systems, electromagnetic trapping, quantum control, precision spectroscopy, and many other fields have all benefited from the demands of atomic clock development. The technologies developed for timekeeping have found applications in quantum computing, precision measurement, and fundamental physics research. From a fundamental physics perspective, atomic clocks are powerful tools for testing basic theories. General relativity predicts that time dilation depends on both velocity and gravitational potential, and atomic clocks have verified these predictions with extraordinary precision. Any deviation from the predictions would indicate new physics beyond our current understanding. Similarly, atomic clocks can test whether the fundamental constants of nature are truly constant, or whether they might vary slightly over time or from place to place. So far, no variations have been detected, placing ever tighter constraints on theories that predict such changes. The precision of atomic clocks also makes them sensitive to certain types of dark matter. Some theoretical models suggest that dark matter might cause tiny oscillations in the values of fundamental constants, which would show up as correlated fluctuations in clocks made from different types of atoms. Networks of atomic clocks around the world are being used to search for these signals, potentially opening a new window into the nature of dark matter. Let's step back and appreciate the remarkable journey that has brought us from the first mechanical clocks to today's quantum timekeepers. Early humans measured time by the rising and setting of the sun, the phases of the moon, the changing seasons. The invention of mechanical clocks in medieval Europe allowed time to be measured independently of astronomical observations, enabling the coordination of activities across towns and cities. The pendulum clock, invented by Christian Huygens in the 17th century, brought a significant improvement in accuracy. Marine chronometers, developed in the 18th century to solve the problem of determining longitude at sea, pushed mechanical timekeeping to new heights of precision. The 20th century saw the transition from mechanical to electronic timekeeping. Quartz clocks, which used the piezoelectric vibrations of quartz crystals, became widely available and brought accurate time into every home and office. But all of these technologies shared a common limitation. They relied on physical objects, whether pendulums or crystals, whose properties could change over time and with environmental conditions. Atomic clocks broke through this barrier by anchoring timekeeping to the unchanging properties of atoms themselves. The first Cesium atomic clock, developed at the National Physical Laboratory in England in 1955, was accurate to about 1 part in 10 to the 10th power. In the 7 decades since, that precision has improved by roughly a factor of 100 million. This astonishing rate of progress, averaging about an order of magnitude improvement per decade, represents one of the most sustained advances in precision measurement in the history of science. The people who develop and operate atomic clocks are part of a small but dedicated global community. National metrology institutes in countries around the world, including the National Institute of Standards and Technology in the United States, the Physikalische Technische Bundesanstalt in Germany, the National Physical Laboratory in the United Kingdom, and many others, maintain primary frequency standards and contribute to the calculation of international atomic time. University research groups push the boundaries of what is possible, developing new techniques and exploring new atomic species for timekeeping. Private companies build commercial atomic clocks for applications ranging from telecommunications to satellite navigation. The work requires a combination of deep theoretical understanding and exceptional experimental skill. Building and operating an optical atomic clock involves mastering a dizzying array of technologies. Researchers must understand quantum mechanics, atomic physics, laser physics, vacuum technology, electronics, control systems, and much more. They must be able to design and build intricate experimental apparatus, diagnose subtle problems, and make measurements at the very edge of what is physically possible. Yet despite this complexity, there is something beautifully simple at the heart of every atomic clock. It all comes down to counting the oscillations of electromagnetic radiation as atoms transition between quantum states. The universe provides us with perfect oscillators in the form of atoms, and human ingenuity has figured out how to listen to their ticking and count their beats. This marriage of natural precision and human cleverness has given us a technology that seemed like pure science fiction just a century ago. As we look to the future, it is clear that the quest for better clocks will continue. Each improvement in precision opens new possibilities for science and technology. Future navigation systems could locate positions to within millimeters rather than meters. Tests of fundamental physics could probe ever more deeply into the nature of space, time, and matter. New applications that we cannot yet imagine will surely emerge as clocks become more precise and more widely available. The story of atomic clocks is ultimately a story about human curiosity and persistence. It began with questions about the nature of atoms and light, questions that seemed purely academic when they were first asked. The development of quantum mechanics in the early 20th century provided a theoretical framework for understanding atomic transitions. Decades of experimental work turned that understanding into practical devices. And now, nearly a century after the first hints that atoms could serve as timekeeping references, we have clocks that can measure time with a precision that would have seemed utterly impossible to the pioneers of the field. There's also something philosophically profound about atomic clocks. Time is perhaps the most fundamental aspect of our existence. Everything we do, everything that happens, takes place in time. Yet time remains mysterious. We cannot see it, touch it, or hold it still. We can only measure its passage. And now we can measure that passage with such precision that effects predicted by Einstein's theories of relativity, effects that alter the very fabric of space and time, become directly observable in a laboratory. When you look at a cesium fountain clock or a strontium optical lattice clock, you're looking at a device that operates at the intersection of multiple revolutions in physics. Quantum mechanics tells us that atoms can only exist in discrete energy states, and that transitions between these states produce light of precise frequencies. Special relativity tells us that moving clocks run slow and that mass and energy are equivalent. General relativity tells us that gravity warps space-time and causes clocks at different heights to tick at different rates. All of these fundamental insights, developed over the past century by some of the greatest minds in human history, come together in the operation of a modern atomic clock. The technology continues to advance at a remarkable pace. Researchers are working on transportable optical clocks that can be moved from laboratory to laboratory for direct comparisons. Satellite missions are being planned to test clock performance in space. where the reduced gravity allows longer observation times and where global comparisons could be made more easily. Networks of synchronized clocks are being developed for applications ranging from very long baseline interferometry in radio astronomy to searches for gravitational waves. Speaking of gravitational waves, it is worth noting the connection between atomic clocks and these ripples in space-time. When a gravitational wave passes through a region of space, it stretches and compresses distances in a characteristic pattern. This stretching and compressing affects the wavelength of light traveling through that region, which could in principle be detected by comparing clocks at different locations. While current gravitational wave detectors use laser interferometry rather than atomic clocks, future ultra-precise clocks might offer a complementary approach to detecting these cosmic messengers. The miniaturization of atomic clock technology is another active area of development. The first atomic clocks filled entire rooms and required teams of technicians to operate. Today, chip-scale atomic clocks, smaller than a sugar cube, are commercially available, bringing atomic precision to portable devices. These miniature clocks use different approaches than their laboratory cousins, often relying on coherent population trapping rather than microwave cavities, but they achieve accuracies that would have been world-leading just decades ago. Even smaller and more efficient atomic clocks are under development, potentially enabling new applications in portable devices and distributed systems. The integration of atomic clocks with other quantum technologies is creating new possibilities. Atomic clocks share many technical elements with quantum computers and quantum sensors. The laser systems, vacuum apparatus, and control electronics developed for clocks can be applied to other quantum devices. Conversely, advances in quantum control from the computing community feed back into clock development. There is a growing synergy among different branches of quantum technology that is accelerating progress across all of them. Education and outreach are important aspects of the atomic clock community. The concepts involved, while rooted in advanced physics, can be made accessible to general audiences, explaining how atoms serve as perfect oscillators, how laser cooling works, and why precise time matters for everyday technology helps build public appreciation for fundamental research. Many clock laboratories welcome visitors and participate in educational programs, sharing the excitement of working at the frontiers of precision measurement. The economic importance of precise timekeeping is often underappreciated. Estimates suggest that atomic clock technology contributes hundreds of billions of dollars annually to the global economy through its enabling role in navigation, telecommunications, and financial systems. This enormous economic value flows from research investments that might have seemed purely academic when they were made. The story of atomic clocks is a powerful example of how fundamental research can lead to transformative practical applications, often in ways that could not have been predicted in advance. As the precision of atomic clocks continues to improve, new challenges emerge. At some point, the clocks become so accurate that they are limited not by the clocks themselves, but by our ability to compare them. Transferring time signals over long distances introduces uncertainties due to atmospheric effects, cable delays, and other factors. Developing better methods for clock comparison is therefore an important part of the overall effort. Fiber optic links, satellite connections, and even very long baseline interferometry techniques are all being explored and refined. The philosophical implications of extreme time precision are fascinating to contemplate. What does it mean to define the second in terms of atomic transitions? We have created a circular reference where the unit of time is defined by a counting process that itself takes place in time. Yet this circularity is not a flaw, but a feature. By grounding our time standard in the unchanging properties of atoms, we have achieved something that was impossible with earlier methods. We have a definition of the second that is, to the best of our knowledge, the same everywhere in the universe and for all time. This universality connects atomic clocks to fundamental questions about the nature of physical law. If the properties of atoms are the same everywhere, then our time standard based on atomic transitions should also be universal. Astronomers searching for signs of life elsewhere in the universe have speculated that atomic transition frequencies might serve as a basis for interstellar communication, providing a common reference that any technologically advanced civilization would understand. Whether or not we ever encounter such civilizations, the idea highlights the fundamental nature of what atomic clocks measure. The development of atomic clocks has also contributed to our understanding of the quantum measurement problem. When we measure the frequency of an atomic transition, we are probing a quantum system, and the act of measurement affects the system being measured. Clock scientists have developed sophisticated techniques for minimizing measurement-induced perturbations and for extracting maximum information from quantum systems. These techniques have applications beyond timekeeping, in quantum information science, and in tests of fundamental quantum mechanics. Looking at the history of time measurement, each major advance has enabled new capabilities and changed how humans live and work. The mechanical clock enabled the coordination of activities in medieval cities, leading to new forms of social and economic organization. The marine chronometer enabled accurate navigation at sea, opening the age of global exploration and trade. The quartz clock brought accurate time to every home and wrist, transforming how people organize their daily lives. What will be the transformative applications enabled by optical atomic clocks with their nearly incomprehensible precision? Some possibilities are already visible. Ultra-precise navigation could enable autonomous vehicles to operate safely in complex environments, knowing their position to within centimeters. Geodetic measurements with clock-based techniques could monitor environmental changes with unprecedented detail, tracking the movement of water and ice across the planet. Tests of fundamental physics could discover cracks in our current theories, pointing the way to new understanding. But history suggests that the most important applications may be ones we cannot yet imagine, emerging from the creative combination of new capabilities with unmet needs. The international collaboration that sustains atomic clock development is worth celebrating. Timekeeping is one of the oldest forms of international scientific cooperation, dating back to the establishment of coordinated time zones and the International Date Line in the 19th century. Today, atomic time is maintained through a network of laboratories spanning the globe, each contributing their measurements to a weighted average that defines coordinated universal time. This cooperation transcends political boundaries and continues even during times of international tension, reflecting the fundamental importance of accurate time to modern civilization. The people who work on atomic clocks come from diverse backgrounds and bring different perspectives to the challenges involved. Experimentalists devise new ways to control atoms and measure frequencies. Theorists calculate the properties of atomic systems and identify promising transitions to exploit. Engineers design the lasers, vacuum systems, and electronics that make experiments possible. Metrologists develop methods for comparing clocks and propagating time signals. The field thrives on this diversity of skills and approaches. For young people considering careers in science and technology, atomic clocks offer a uniquely rewarding area of work. The field combines fundamental physics with practical engineering, offering opportunities to contribute to both basic knowledge and useful applications. The precision involved is extraordinary, pushing the limits of what measurement can achieve. And the applications are genuinely important, underpinning technologies that billions of people use every day. Working on atomic clocks means being part of a tradition that stretches back to the earliest efforts to measure time and forward to applications we can barely envision. As we approach the end of our exploration of quantum clocks, let us reflect on what makes these devices so remarkable. They represent a triumph of human intelligence over the challenges of measurement. They demonstrate that nature provides us with perfect reference standards if we are clever enough to use them. They enable technologies that transform daily life for people around the world. And they continue to improve, with each generation of clocks more precise than the last. The atoms at the heart of these clocks are utterly ordinary. Cesium, strontium, ytterbium, aluminum are elements that exist throughout the universe, formed in the hearts of ancient stars. Yet by understanding the quantum properties of these atoms and developing the technology to probe them with exquisite precision, humans have created time-keeping devices of almost supernatural accuracy. This is the power of science, to take ordinary materials and ordinary phenomena and, through understanding, create extraordinary capabilities. The story is far from over. Researchers continue to push precision higher, to develop new types of clocks, to find new applications for existing clocks, and to address new challenges as they arise. Each improvement opens new possibilities. The next breakthrough might come from a large national laboratory with massive resources, or from a small university group with a clever new idea. The international community of clock scientists continues to grow and diversify, bringing fresh perspectives to ancient questions about the nature of time. When you next check the time on your phone or computer, consider for a moment the chain of technology that makes that simple act possible. Somewhere in laboratories around the world, atomic clocks are ticking with almost perfect regularity, their frequencies locked to quantum transitions in carefully prepared atoms. Signals from these clocks propagate through networks to synchronize computers, telecommunications systems, and navigation satellites. The time displayed on your screen ultimately traces back to the unchanging properties of atoms, properties that have been the same since the beginning of the universe and will remain the same until its end. This is the gift that quantum clocks give us, a way to measure the most fundamental dimension of our existence with precision that approaches the limits set by nature itself. A window into the quantum world, where particles exist in superposition and transitions occur with perfect regularity. A tool for probing the deepest questions about the nature of space, time, and matter. And a foundation for technologies that have transformed how we live, work, and navigate through the world. The next time you hear someone say that a meeting will start at a certain time, or that a package will arrive within a certain window, or that a financial transaction occurred at a certain moment, remember that these everyday conveniences rest on the most advanced technology for measuring time ever created. Atomic clocks are hidden infrastructure, invisible to most people, yet essential to modern life. Understanding how they work and why they matter enriches our appreciation of both the science involved and the technology that shapes our daily experience.